crystal. Now this is another interesting thing you can do. We can make 90-degree bends. So take one rod out, this green part, yellow part, that becomes a waveguide, defect waveguide. Take another rod out that is orthogonal to this rod, but there are no orthogonal rods on this plane. So we take one in the below. You can see the yellow, right? So those two are taken out and create a defect waveguide of the shape of an L. Let's start again. And this is what happens when you feed that L from one end. Field propagates along the top waveguide. The configuration is like here, rectangular waveguide, then coupled to the defect waveguide, and keeps propagating, and then it gets to this junction, the bend. Normally, in a lot of waveguides, if you do that, you get a lot of reflections from that point. But in this type of waveguide, instead of coming back, it jumps to the lower level. You can see it's one level down. It jumps to the lower level, and it propagates through the lower level defect waveguide, that is this yellow part, and then comes out from the other end. So you can get very good transmission again with very little reflection from this kind of sharp bends. This is quite useful in optics because you can't make 90-degree bends in fibers, optical fibers. If you bend the optical fiber, because optical fiber operates based on total internal refraction, right? Total internal refraction. That needs a reasonably straight fiber or a large curve of radius. If you bend it to a very small curve of radius, then the internal total internal refraction doesn't work. You get light leaking out. So people created photonic devices like this, photonic integrated circuits with 90-degree bends with this concept. This is another interesting thing. You can actually make something like a 1D horn by modifying only one layer in the photonic crystal or EBG structure. And all the other layers are the same. We modify only this layer and we deform it to create something like a horn. And then when we apply a wave to the input waveguide, again it couples nicely to this defect horn instead of reflecting back, and it propagates along the horn and spreads here. And this is the end of the crystal where it radiates into free space with minimal reflections. So this is totally dielectric photonic crystal or electromagnetic band gap wave horn antenna. And you can make arrays of these horns. One group in Spain, in Pamplona, asked us to collaborate with them, and then they make these horn arrays, the two horns, one above the other, evanescently coupled, so that they can get a narrow beam on both planes. This horn is just because one-dimensional. It has a narrow beam on the vertical plane. It has a narrow beam on the horizontal plane. The vertical plane, the beam of this horn is wide. because the horn has a very short aperture in the vertical plane. Because of that, the radiation pattern is very wide. But when you have two or multiple horns in an array in the vertical direction, you get the array effect. So you can narrow the beam on the vertical plane as well. So you can get a narrow beam on the vertical plane due to array effect, and also in the horizontal plane due to this horn effect, creating like a narrow pencil type beam. So those are some of the electromagnetic band gap work. I did not present all of them, just to give you an idea. There's one more EBG I want to show you because it's one-dimensional circuit type structure. So electromagnetic band gap, as I said, can be the whole structure could be one-dimensional, two-dimensional, or three-dimensional. We had only very little work on 2D type structures. They are mostly photonic structures. But this is one of our 1D research. So it's a periodic structure, as you can see, periodic waveguide in one dimension. A little like a leaky wave antenna, but it's not a leaky wave antenna. It's just a transmission line, periodic transmission line. What you're trying to do here is to create a band gap that can be reconfigurable. So this is an active device. The configuration is fairly simple. It's a transmission line and some patches with the ground plane. These are the patches. This is the microstrip line. These are the patches underneath. And then they are connected through vias to a down plane. And here, there's some spacing where you can put switches, controllable switches, like the pin diodes in the previous example. So they are binary switches. And so this patch is not connected to the ground plane. This patch is permanently connected to the ground plane through these vias. And this one, this is what actually we wanted to do, is connected when the switch is closed. Both switches are closed. The via connects to the ground plane. When the switch is off, via is not connected to the ground plane, so this patch floats. So it's a binary device. Sometimes when the switches are closed, it operates like this. When the switches are open, it operates like this. Binary switching pattern across the device controls the band gap. So we prototyped this at microwave frequencies using MACOM commercial gallium arsenide FET switches. And we also made a millimeter wave integrated circuit MMIC gallium arsenide device at millimeter wave frequencies. So this is our device, 1D EBG. There's a lot of things here because all these switches need to be binary switches, so it needs control, bias lines and all that, right? So a lot of these extra things are bias lines, and they're totally digital control, under digital control. This is the band gap. These are the electromagnetic effect of this. This is S21, the scattering parameter. That means it's a transmission from one end to the other. Like that's transmission. And you can see that when all the switches are open, it's more like a transmission line. It's not like a filter. Transmission is more or less the same across the whole band. Yeah, some frequencies are bad, but it has reasonable transmission. However, when all the switches are 1-1, that means 1-1 means all the switches are like 1-1-1-1-1 closed, then the band gap would be like shown in the green. So it's a filter, right? It's a filter. It stops transmission in this band. So quite wide band. But the real beauty is this cutoff, which has very, very fast cutoff versus frequency. And then with other switching patterns, like 1-0 is the purple one, the band gap is only this much. So it's a controllable variable filter with a controllable band gap, active device. So those are sort of things you can do with EBG. Okay. So now, because we have about 45 minutes left today, and I promised to do the leaky wave today, the leaky wave antennas. I know you have already done some leaky wave presentation yesterday. There may be some overlap, maybe not. I don't know what was presented yesterday, so I will start this was a IEEE distinguished lecture on leaky wave antennas. I presented in some places. So before that, again, are there any questions on the topics we discussed so far?
So participants, if you are having any queries, you can ask in between.
So this was also a keynote speech in a conference called ISCOM, that is usually in Europe, and that year it was in Croatia. So these are the topics. What is a leaky wave antenna? Very basic, and then one specific type of leaky wave antenna is called half-width microwave leaky wave antenna. Uniform and quasi-periodic half-width microwave leaky wave antennas. Periodic half-width microwave leaky wave antennas. Dual side beam leaky wave antennas. Fixed frequency leaky wave antennas. And then the fixed beam arrays of uniform half-width leaky wave antennas, and composite right and left hand leaky wave antennas. It's quite a bit. I will try to go. Are there any of the topics we discussed yesterday, so I can go faster, or should go in the normal pace? I can do either way.
In the last lecture, the basics of the leaky waveguide antenna and some antennas were shown by Dr. Prasad.
Right. Okay, let's see. They may be different. So this is a typical water hose, right? Normal antenna is like this. You have a transmission line or waveguide, and then you have a horn antenna or any other antenna that radiates at the end. So that's normal antennas are like this. Rectangular waveguides, and if you connect the antenna to the end, microstrip line with is like this hose, no leakage. The hose is like waveguide. At the end, the nozzle is like an antenna. Now, leaky wave, this is a leaky hose, right? You may have one hole or several holes along the hose. And leaky wave antenna is more or less like this. It is an antenna, or it's a transmission line that leaks radiation along the length. So you can consider it as a pretty bad transmission line with holes in it that leaks. But from antenna perspective, it's pretty useful antenna. So what happens when you apply energy, electromagnetic energy at one end of this leaky transmission line? One of the examples of the leaky wave antennas is this leaky wave antenna published by Olina, etc. That is just a waveguide with a slot on the side. Because this slot, the currents on the waveguide wall are vertical, and this slot interrupts these currents and radiate on the side, and that becomes a leaky wave antenna. Normally in leaky wave antennas, usually we terminate the other end of the transmission line by a matched load, and we apply in a microwave signal at one end. So it propagates. While it propagates, it leaks. Therefore, the amplitude drops exponentially. And this is probably the part you already learned yesterday. The leakage factor, etc. It's proportional e to the power minus gamma. I said that the gamma propagation constant is alpha plus j beta. Alpha is the attenuation constant, beta is the phase constant, and so on. So what happens if the decay is very sharp like this? Then there's almost nothing that would reach the end, right? So there's nothing that's going to dissipate in the match load, because that's going to be waste. Normally, we don't want a lot of energy going to the match load. We want most of the energy radiated by the leaky wave antenna. Very small amount reaching the match load. However, there's another problem if it decays very fast, like this. So when the attenuation constant is very large, like alpha is large, it decays very quickly. So you see the field only in this small section. So the effective aperture of the antenna is very short. And we know the result of that, right? When you have small effective aperture, you have less directivity. It's like a smaller antenna. Less directivity and less gain. So this is not an ideal decay because it's very short, effectively short. On the other hand, if it decays very slowly along the length and still have a reasonable current and energy at the end, that energy goes to the match load and dissipate. So that is a loss. But its effective length is long, so it has good directivity. Its effective length is long, so it has very good directivity. But because you're losing energy here, power, efficiency is less, radiation efficiency is less. So remember in the first equation, I said gain is directivity times efficiency. So the directivity is high, but gain is not equal to or close to directivity, but it is a bit less. The gap increases. So you want to design good leaky wave antennas depending on your application somewhere in between. It won't decay very fast, too fast. Sometimes you want it to decay at a certain rate. So that's how you set the alpha in the design. Okay. So what are the properties why we are interested? It's a wideband antenna that radiates a narrow beam, especially if you have a large aperture. Beam direction of a conventional leaky wave antenna changes with frequency. Probably you heard it yesterday. It has excellent bandwidth, simplicity. You can, the old ones, the old leaky antennas are like on waveguides, so they are not very easy to fabricate, but these are printed circuit boards, like a microstrip line, right? It's very easy to fabricate using printed circuit board technology. Planar, low profile, simple. Then limitations. To steer the beam of these antennas, you have to change the frequency. That is one problem. And in some applications, you can't change the frequency. Frequency is determined by regulators. In a Wi-Fi system, the frequency has to be within this band, and you can't just keep it changing it. Another problem, uniform leaky antennas cannot radiate in the backward, broadside, or end-fire directions. And there are some ways to overcome these limitations, and we are going to look at it today or tomorrow. Okay. Now I will let me introduce the half-width microwave leaky wave antenna concept. This is a normal microstrip line type, and this is the fundamental mode of a normal microstrip line, electric field lines. You are all familiar with that, I suppose. We are going to skip this mode, go to the next mode, first higher order mode. This is the first higher order mode. You can see that electric field is going up on this side, going down on this side. And there's a null in the middle. So this is the mode we are going to use. And because we have a null in the middle, you can put a VR or a shorting wall or a septum along the middle, and it will not short circuit anything because there's no electric field along that wall. So it will not change the characteristics. Now the other interesting thing we can do is, because this is a symmetrical structure, we can chop it half. We only need half of the line. So we need, we need only this. We don't need the whole. We need only half width microstrip line with the via or shorting wall. It could be, shorting wall could be a straight continuous wall along the middle, but that is difficult to implement sometimes. Or septum, continuous septum. One way to do it is in a lot of vias very close to each other. So this is basically a half width microstrip transmission line, and it can be used as a leaky wave antenna. Now the equations, I'm sure you saw this yesterday. The beam direction theta is determined by sine inverse phase constant beta divided by k naught. Beta is a function of frequency. K naught is also a function of frequency, that's wave number. Linearly increases with frequency. But this is not a linear function of frequency with zero intercept. So when we divide this by this ratio becomes frequency dependent. It changes with frequency, and therefore the beam direction also changes with frequency. That's why you can steer its beam by changing frequency. And that's kind of universal for almost all leaky wave antennas. So let's get to examples. This is a uniform leaky wave, half-width leaky wave antenna. That's the half-width microstrip transmission line. This is the septum on the top, either continuous or made out of vias. And then you need to match this with 50 ohm input lines. They are coaxial. So there's a there's a fairly interesting tapered line and the matching section. And that's about it. So that's basically the whole antenna. So we feed it at one end, we connect the other end to a matched load. Both ends are 50 ohms, so we connect this to 50 ohm match load. We feed from this end. And this example is a real design of Rogers substrate, fairly thin, and so on, the other parameters. These are all in publications, so you can find the details. I will give you the references. Now, how do you analyze this? You can analyze using an equivalent circuit model for simple analysis. A standard microstrip line section, a little section of a microstrip can be modeled by a linear inductor and a parallel capacitor, right? It's the normal transmission line. We assume lossless. That's a small section, and then we can cascade that to model the complete transmission line. Now we have a different microstrip line with the septum and vias. Septum is, not septum and vias. The septum is can be implemented using vias. It's the same. It's a vertical wall shorting the microstrip to the ground plane. So that's the top view. This is the cross section. So because of that, we need to add extra inductance of the septum inductance to the shunt capacitance. So the shunt component becomes parallel capacitor and inductor, whereas the series is just the inductor. So that's the equivalent circuit model for this half-width microstrip. Then you can analyze that and work out the other details. So I'm jumping ahead and showing you typical radiation pattern of a uniform half-width micro leaky wave antenna for different frequencies. These are actual gain patterns for different frequencies from 4.2 gigahertz to 5.8 gigahertz. Lowest frequencies, this gain is around 10 dBi, and the beam direction is around 23 degrees. And when you increase the frequency, the gain increases and decreases then. And when you get to 5.8 gigahertz, the beam direction is about 69 degrees. So by changing the frequency, you can change the beam direction. There is some variation in the beam width and the gain and directivity as well. The other thing is this kind of very simple uniform antennas cannot radiate in the bow side or broad side direction, that is theta equals 0. So it's only radiating on this side. Then this is a periodic U-slot loaded half-width leaky wave antenna. So the difference here is along the transmission line we have U slots. So it's loaded by U slots. Can see them better here, I guess. This is the actual photo of a prototype. The other parts are the same. We have SMA connectors at the two ends, the substrate, microstrip, The septum, instead of a continuous septum, we implemented it using array of vias, and the main difference is these U slots on the top. We published this in Attribute Transactions in Antennas and Propagation, so this is 2015. First author is my PhD student at that time, Karmakar. He is now an academic in University of Western Australia. He has written a lot of papers in this area. He's still working in this area. He still collaborate in some related work. Now we have to develop an equivalent circuit for this, right? So let's break it down to a few sections. There's a part that does not have U slots, and then there are parts that has U slots. So the part that does not have U slots is just like this. The half-width leaky wave antenna with vias. And that section can be described by our equivalent circuit that you saw before. Exact the same linear series inductors and parallel capacitor and inductor. Then the next section has U slot. The U slot adds additional capacitors to the series element. So this is again, now it is also a parallel combination of L and R. This is also a parallel combination of L and R as before. Then the next section is again uniform no slot. So this is the same as that block 3. So block 1, block 2, block 3. In 3 blocks, you can represent the unit cell of this antenna, considering it as a periodic structure, right? It's a 1D periodic structure, but it is not lossless. We assume the material, metal and dielectrics are lossless, but because it's radiating, it's not lossless. Its loss is actually the radiation loss, if you want to call it a loss. But it's a good loss because we need that. So to make the dispersion diagram of this kind of circuit is not difficult. There's analytical formulas. We use the equation I showed you before to find the beam direction. And this beta is determined by A and D parameters of the ABCD matrix of this unit cell. Now, ABCD matrix, if you are not familiar, normally you can find these things in the appendices of textbooks, like scattering parameters, Y parameters, X parameters. These are all two-port network parameters. ABCD parameters are another type of parameters to define voltages and currents in a two-port network. So this is fairly simple two-port network. This is the uniform section without the slot. So for this kind of section, ABCD parameters are determined by series inductance and the shunt, series impedance is Z and shunt admittance Y. YU represents these two together. ZU is only this inductance. So ZU is just the impedance of the inductor, that's J omega L, and Y is the shunt admittance, that is the sum of the admittance of these two. So when you do the maths, you get this equation. So you can substitute all these things in the equations, and you find that A is very simple, is equal to this, D is equal to 1, and you substitute this here, you get beta. And you substitute beta here, you get the beam direction for any frequency. So this is after substitution. Beta is given by this analytical equation. Now, if you want the numerical values, you can substitute values of these inductance and capacitances. These are some example values. When you substitute that, you get beta, the phase constant versus frequency. In fact, here we plot frequency versus beta. The phase constant beta is this axis and the frequency is this axis. These are for 3 different sets of inductors and capacitances. Just focus on only one, like this red curve. That's for one set. So this is how the phase constant varies with frequency in this antenna. So for each frequency, there's a different phase constant. And because of that, when you substitute that phase constant in that equation for theta, you get the beam direction, different beam direction for different frequency. Okay, now there's another thing here called airline. Is anyone familiar with the airline? This is a term used in these dispersion diagrams. That is very important because sometimes this line does not radiate.
Sir, your voice is not coming. I think you have muted yourself.
My computer muted myself. I will pull this to the side so I can see the warning. Okay, so let's focus on the red curve. We change the frequency and we get different beta values, and that means different beam directions, right? But we are above the airline, so it radiates like a leaky wave antenna up to this point. After that, it stops radiating, and after that, it's just a transmission line, not an antenna. So this intersection between the dispersion curve and the airline is important. So there's a lot of mathematics in this, how to calculate the starting point, the frequencies F1, that is where it starts behaving like a leaky wave antenna. Fairly simple equations. And F2, that is when it stops, but it does not work up to this frequency, right? Normally, leaky wave antenna radiation stops here. That's the formula for that. You can derive all these things. And then you can create the ABCD matrix for the whole unit cell. This is the part that does not have the U slot. This part has the U slot, and this part doesn't have the U slot. It's several sections. So you take the ABCD matrix of this section, this section, this section, all 6 sections, multiply them together to get the total ABCD matrix of this unit cell. And you can derive these equations to find A and D. Those are the only 2 important for us. of that unit cell. Substitute that A and D in the equation for beta, so you get the phase constant versus frequency, the dispersion diagram for the leaky wave antenna with slots, with U slots. The previous one was without U slots, and this one is with U slots. I can see that it is a different dispersion diagram. It actually has 3 bands. It actually has 3 bands. Why I say that? Look along the frequency axis. This red curve is a dispersion diagram for the lowest band. It starts at this frequency, goes up to here, and stops leaking. Then in this band, it does not operate in this gap. Then at this frequency, it starts leaking again as a leaky wave antenna. So we keep changing frequency, increasing frequency, it will operate up to F2 here. Right? That is if you use the parameters for the red parameters, red set of parameters. If you use this set of parameters shown by the black line, the first band starts here and operates up to this frequency. Then there's a gap. It does not operate as a leaky wave antenna up to this frequency. That's the airline intersection, and it operates all these frequencies up to F2. And then there's a narrow, very narrow gap. It does not operate. And then the third band starts at F3. And this is the third band, which basically a dual or triple band leaky wave antenna with 3 bands, 3 radiating bands. And the equations for F1, F2, F3 are these. So a lot of mathematics, quite boring. I will skip that and go to the props. And these are the dispersion diagrams. This is used in the equivalent circuit. Dispersion diagrams like the one we saw before, and these are the gaps. There's no leak wave here. It starts at this frequency and radiates up to this frequency, and that is the lower band leaky wave right hand region. Then there's a gap. The antenna does not operate, does not radiate in this band, and then it starts radiating again. This is a left hand region from here up to here. And then the third band is not shown here for this particular set of parameters. Now this is using the equivalent circuit parameters, but if you use simulation program like CST, eigenmode solver in CST Micro Studio, or I think ANSYS HFSS has eigenmode solver as well. You don't need the equivalent circuit. You can simply simulate the unit cell and find these bands. So the first dispersion band here, the second band is here. First operating antenna band, these are all from CST. Is from this frequency, right hand region that provides forward radiation in one direction, and then there's a gap within which it does not radiate, and then this is the other region higher mode, higher band, and it radiates in a different direction. I will show you this direction. So these are the radiation patterns, normalized patterns. This is the lowest band. Predicted and measured radiation patterns. So we build the prototype and measure the patterns on the XZ plane at different frequencies, starting from 5.25 gigahertz, that is this. The peak beam, you can see the beam direction theta around 30 degrees. Then we increase the frequency up to 6.25 gigahertz, that is this. Now the beam direction is about 60 degrees, right? So beam direction change from about plus 30 to gradually to about plus 60. So that is beam steering by change in frequency. Then from 6.25 to 7.75, so it doesn't work as an antenna. Then at 7.75 gigahertz, we have quite different radiation pattern. That is the normalized pattern. The beam direction is something like minus 40, 50 degrees, negative in the other direction. And we keep increasing the frequency up to 9 gigahertz. Now the beam is moving from negative theta towards less and less negative theta, and here it is about minus 15 degrees, right? From minus 40, 50 to minus 15, 20 as we increase frequency. And these are the radiation patterns, simulated radiation patterns in CST. And this is the lower band. It's radiating in one direction, positive theta direction. The peak is in red. You probably can't see the frequency. These are lower frequencies, 5 gigahertz, 6 gigahertz, etc. Then this is the upper band. You can see that, and this is increasing with increasing frequency. The beam direction changes. So this is beam steering by change in frequency. In both cases, we are increasing frequency, but this is the upper band, starting 7, 8, 9, and so on. So with very negative value to less negative value in the beam direction. These are some of the parameters. The lower band 5.25, 6.25 gigahertz. The measured beam direction starting from plus 30 to plus 65. That's what you see here. Plus 30 to plus 65. That's the measured beam direction. These are the predicted beam directions using different methods, equivalent circuit method, eigenmode simulation of one unit cell, and this is full wave simulation of the whole antenna using CST. This is just one unit cell. So you can find reasonable, even these models can predict the beam direction to some extent, sometimes this larger discrepancy, and the cross-polar level, etc. Then this is the upper band, change in frequency from 7.75 to 9, increasing frequency, beam direction starting from minus 46 degrees, that's minus 46, going up to minus 10 degrees. Okay, that's very clear presentation of how the beam steers with frequency in a dual band periodic leaky wave antenna. Now, if you plot this, now this is the third band. So those are the two bands. And then, so remember, in sometimes you have a third band, right? Even higher, like 11 gigahertz to 15 gigahertz. That's the third band. This band goes from negative to positive beam directions, but there's a problem when we get to around 0 degree. That happens around 11.5 gigahertz. You can see the drop in directivity. So the radiation efficiency is high throughout the operating band, even in this band, in the third band, except near the frequency where the beam points towards the both side direction. That is this frequency. So you can see the loss of radiation efficiency. So directivity is high in both backward and forward directions. This is directivity. This is the backward direction, the forward direction. However, it decreases when the beam is along the bow side. So gain is directivity times radiation efficiency. Therefore, gain is even less, pretty bad in the bow side direction. There's a lot of theory on this effect of some leaky wave antennas. Uh, Professor David Jackson, etc., published a lot of papers on this. So this is our paper in IEEE antennas and wireless propagation. Let us forward and backward beam steering, beam scanning, tri-band leaky wave antenna. More details about this. So I have a few other different types of leaky wave antennas, but now we have only how much time left? Let me check this. That's my time. 5 minutes. I think we can discuss. If you have any questions, we can discuss those in the next 5 minutes, and we can finish this leaky wave part tomorrow, and then we start the resonant cavity antennas tomorrow. Any questions?
So the platform is open to all. You can ask your queries.
So this is
I think there is no query, sir.
okay. I will show you. Probably I should have the list of references at the end. Not all of them, but some of them. If you want to read anything about this, you
Sir,
can take.
one query is there from
Yeah.
Swati Patil.
Okay.
Swati, you can ask by just turning on your mic. Better to join with your email ID that was provided with us. As you have joined as a viewer, we have already created you as an contributor there. Or you can write in the chat box.
Yes, I can see the hand, but I don't hear anything.
Swati Patil, if you are having query, you can write in the chat box.
You could
I
try
will
to.
I will convey if the query will come to me, sir. I will convey to you, and
Okay.
we can
Yeah.
resolve that question in the next the tomorrow.
Yeah. So yeah, we stopped here. So tomorrow we will look at few other different type of leaky wave antennas, and also the fixed frequency beam steering. Because when you don't have the option of changing the frequency, your frequency is fixed. How do you steer the beam? Then you have to change something else, right, to steer the beam. And there are ways to do that too,
Hello.
using various reconfigurability methods.
Hello.
If there are no other questions, so I will stop it
There is
today.
one question from the
Yeah.
Swati. She asked directly to me that
Okay.
how is the equivalent circuit is made for the leaky wave antenna?
Okay. It's partly theoretical. The theoretical part is by looking at the physics and modeling. Okay, there's a capacitor here, like I explained. Each part, this capacitance is the capacitance created by the U-shaped slot, and this inductor is the inductor of the via or septum, and so on. But how do you pick the values? That is difficult. That is quite difficult. So you can use simplified analytical equations for inductance, etc. The other way to do it is do a curve fit. Once you have some measurements or the simulated results, you can go back and actually work out the equivalent circuit parameters because you know the response. So the circuit can be developed by theory, but the finding values for the circuit parameters is difficult. That is the case with a lot of other equivalent circuits too, right? So I'm not these days where people don't use equivalent circuits, only to use it to understand the physics. If you change these parameters, this frequency is going to go up, and so on. You can understand the trend, but for actual design, it is less useful. It's useful to understand the physics, but it's less useful to design direct simulations, either unit cell simulations using eigenmode solvers or full wave simulations in CST. That is the way we design these antennas.
The one more question is there that
Yeah.
which tool is used to make it?
Sorry?
Which tool is used to make it?
This is standard printed circuit board method because there's nothing people here use radio frequency printed circuit boards can make this. See, there's nothing.
Hello, sir. Can I ask a question? Hello, sir.
You are audible as Durga. You can speak loudly. You were audible there.
Yes, sir. Sir, I don't know whether it is evening or night for you, sir.
It is in
It's
the night.
very.
It is around 8.
It's 8:30 p.m.
Okay, sir. So, sir, I am Padmaja, and my question is.
You have to speak a little bit louder because my speaker is very, very faint.
Okay, sir. Sir, in all the research works, whatever you have
Kindly speak louder.
Yeah, I can't hear you.
You are audible, but speak loudly.
Close to the microphone.
Close to your microphone.
Yes. 1 second.
S. Durga.
1 second, sir. 1 second.
Actually, your voice is not audible. Kindly come closer to your microphone, or you
Now,
can write in the chat box.
Oh, that's good.
Yeah,
Yeah.
now it is good.
sir, my question is, I have seen a fabricated prototype which has two ports. Like one is the input port, the other is the output port.
Yes.
So it is actually a two-port network.
Yes.
And I feel like it is a two-port network or a kind of transmission media rather than an antenna. Correct me if I'm wrong. I also understood it this way, like it has a two-port network as well as it is a microstrip line. So there can be some radiation from the microstrip line. So that is how it is called as leaky wave antenna. Is it so, sir?
It's a two-port network, but we don't want the reason you have a mesh load at the end. Normally, we don't leave it open this end.
Okay. Okay,
We
sir.
mesh terminate. We put a mesh load to that end.
Okay.
And the reason is if there's some energy left that did not radiate, we want it to be absorbed by this, not reflect back.
Hmm.
So yeah, it's theoretically two-port network, but we don't want it to behave like a two-port network. We want most of the energy transmitted, radiated, and
Along the contact.
very little absorbed by the mesh load.
Okay, sir. Thank you. I am new to this domain, so that is why this would be a fundamental question, but this is my point of concern. Thank you, sir.
You're welcome.
Any other query? I think, sir, we don't have any other query.
Okay, very good. So I can have my dinner.
Yeah, sure, sir.
And you can have your afternoon tea.
Yeah, thank you.
And see you tomorrow.
Yes, sure, sir. Thank you so much, sir, for your wonderful lecture.